So we have here a complex number z. And what we know about z so far is that we could write z in this form: a plus ib. Or perhaps we can write that as x plus iy. So we're using the coordinates x and y. And what we're going to do is turn this into a CIS or polar form. Okay, so CIS form. I'll explain what that is in a minute. But first of all, we've got a z number here, which has a modulus. And the modulus is simply this number squared plus this number squared. So for this particular one, it will be the square root of 18, and then we square root 18, which is 3 root 2. And we call that the r. And so that's here, r. Now I'm going to replace the x coordinate here by thinking about a straight line along here. And I'm going to do the y one as well. So the x coordinate, that can be written as cosine theta, where theta here is the argument. That's equal to the adjacent, which is x, divided by the hypotenuse, which is r. So this gives me x equal to r cosine theta. I'm going to do a similar thing with the y value here. So this is now x and this is y. And what I can do for this is I can say that sine theta equals y, opposite, over the hypotenuse. So we have a similar thing here, which is y equals r sine theta. Now we did a similar sort of thing with the unit circle. So both of these can be replaced in here. So I can now write z as r cosine theta plus iy, and y is being replaced with this long thing here, which is sine theta. And therefore, we can take the r out and we can write that as cosine theta plus I sine theta. And then I can replace that with r CIS theta. So the CIS standing for cosine I sine. And if we go back and look at this one, our theta here, because this is 3 and this is 3, our theta here is pi over 4. The r value we've already worked out. For our particular one, we could actually write z as 3 plus 3i. But we can also write that as 3 root 2. That's my r value. And then I just abbreviate the rest of CIS pi divided by 4 because our theta is pi over 4.